Let's see. Be right back. Okay, let's see. Okay, let's get started. So, you know, I I tend to, it's better if you just unmute yourself and ask a question if you have questions. So you can all see my screen right now, right? So let me go to notes. Okay, can you all see like my notebook right now? Okay, yeah. Okay, cool. So I guess before we get started on actual algebra, I guess what I'm planning on doing again, she said Thursday is quizzes, right? Um, so you'll have one every week. So he did say midterm is on Wednesday of week 3. So I might ask him if if quiz is necessary on that week. So the point of the quiz is just to make sure you're caught up with material. Yeah, the point is I'm not gonna make it like really hard. In fact, it should be pretty easy. So the whole point is just to make sure you're not behind, right? Because this is a 5 week, a 10 week course condensed to 5 weeks. So that being said, again, I'm planning on having a 12-hour interval. So is it fine if I, maybe like, so what I plan to do is upload a PDF to file section, right, with like the questions, and then maybe, however you want to write it, write it on paper, write it on iPad, and then you upload answers to Canvas. So for this, I'll have a trial run. Yeah. So I'll post quiz 0 sometime today, right? it won't count for your grade, but just so you don't encounter any technical difficulties. So, I mean, quiz 0, I mean, just maybe it'll be like write your name or something, but like, yeah, so it'll just be that, practice uploading a PDF online. And then, yeah, and then I guess your first quiz will be Thursday. So I'll tell you like what the quiz will be on, like Wednesday discussion. Yeah. So any questions so far? So, okay. So without further ado, let's get to, okay, right. I forgot to say, is 12 to 12 okay? Like 12 a.m. to 12 p.m. Thursdays? Or I guess it should be 12 p.m. to 12. Let's write it like this. 12 p.m. to like 11:59 p.m. Thursday. I hope I didn't mess this up, but yeah. So you have like 12 hours to do it. Hopefully that all works for you. For whatever. Probably like 2 or 3 is gonna be like, hey, I mean, I feel as long as you the question should not be too hard. Yeah, I'm not, it should be pretty simple. So yeah, it'll just be like testing you on like definitions and stuff. So no hardcore outside the box thinking type of questions. So any questions? Okay. So today we'll just, he told me to go over symmetries and Euclidean division. So before that, I guess people had questions on equivalence relation, right? So let's maybe we should go over examples of that. And in fact, there's a pretty common example. But so let me just go over it. The book he refers to uses like Cartesian products, but most people normally just write tilde. So an equivalence relation tilde is on a set, right? Is any relation satisfying the 3 properties, right? So we have x is equivalent to x, so this is reflexive property. X equivalent to y means y equivalent to x. This is symmetric property. And then transitive property. So y equivalent to z means that x is equivalent to z. So maybe instead of, before I give an example, it's best to give something that's not an example. So if I define x tilde y for, let our set be z, be the integers. If I define x equivalent to y means x bigger than y, is this an equivalence relation? Does it satisfy 1, 2, 3? Most people just type the answer, or you could say it out loud. So is x equivalent to x? Is x bigger than x for any integer z? So for 1, we have to check this, right? This is no, right? So hopefully that's no. Yeah. Okay. And 2, x bigger than y, if and only if y bigger than x. Forget both ways, right? It doesn't even work one way, right? No, if x is bigger than y cannot be bigger than x, right? Luckily, the transitive property works, right? If x is bigger than y is bigger than z, then x is bigger than z, yeah? But if the question is this an equivalence relation, you just stop here, right? you stop like right here. It doesn't satisfy the first property. So you're done, right? To be an equivalence relation, you have to satisfy all three. Oh, sorry. Yeah, I play Fate Go if you're interested. Okay, so continuing on, let's do an example, right? Remember he said A is equivalent to B if and only if A minus B is divisible by 3. So this is part of a bigger class of equivalence relation called modular arithmetic. So what we say is, I think the better example, let's do is the clock. So A is equivalent to B if and only if A minus B is divisible by 12. So when we write this, we normally write this. A is congruent to B mod 12. In general, it's mod n, right? So it means that they have the same remainder when dividing by 12. So I promise you are all used to this. So let me ask you first, what are the possible remainders mod 12? So from here, I'm taking my set to be the integers. So what are all possible remainders mod 12? I mean, when you divide by 12. Huh? X is equivalent to X, right? I mean, if I give you any number, 13 is equivalent to 13 mod 12 because they both have the same remainder. Sorry. I guess I want to say going to be if and only if. Oh yeah, sorry. A and B have not divisible, same remainder. Mod 12. I guess it's not really what the example he gave. I guess it's a different example, but but this is an equivalence relation, right? If you have the same remainder, right, then obviously the equality holds. It's reflexive and symmetric. So here, this is pretty important, right? Because you've all done this, right? If you go to like a different country and someone tells you instead of, because some countries don't use AM, PM, right? They might tell you 23 o'clock, right? Like when you see this, you immediately say 11 o'clock, right? You may think, oh, 23 means 11. But what are you actually doing? You're taking remainder when dividing by 12, right? So you see that 23 is equivalent to 11 because they have the same, remainder when dividing by 12, right? So you can see that here, like it's an equivalence relation, and not only that, we could describe what it is, right? So if I say a class, I think he didn't go over this yet, maybe, but we could separate the class. A class is a representative, right? So where we say the class of A is equal to the class of B if and only if A is equivalent to B. And what you're going to notice is equivalence relations partition integers, yeah? So what do I mean by that? So equivalence relation, partition your set. So in this case, partition your set. So in this case, right, it partitions Z, right? It partitions our integers. So what I mean by this is what is a class? Well, we have the class of 0. We can have a remainder 0, remainder 1, remainder 2, all the way to remainder 11. Yeah. And what partition mean is every integer belongs to one of these classes, right? I mean, when you divide a number by 12, it has to have one of these remainders, right? So what partition means is in this case, I don't want to define it yet because I don't think professor defined it yet, but it means that in this example, every integer belongs to one of these classes, right? Hopefully that's clear. And not only that, it can only belong to one, right? you can't have remainder 2 and remainder 3 when dividing by 12, right? It can only belong to 1. Right, so yeah, so obviously you didn't have to choose this, right? So I just chose 0 to 11. Some people can choose 12 to, I guess, 23, but it's just one element, right? So for example, the class of 23 is equal to the class of 11. Yeah, I think some books write 12 here to denote modular 12, but hopefully, you all see that. So moving on, he wants me to go over Euclidean division. So who here has heard of, Euclidean division? I think it's gone over in maybe Math 140. I don't know. So basically, let me just write, the question comes up, right? If I give you two numbers, this is actually pretty cool if none of you have seen it. Two numbers, A and B, can, I guess AB. I'll write A, B, and D. A, B, and D. Does there exist, hopefully you're on the element, does there exist X, Y in the integers such that AX plus BY is D? So we're kind of going a bit into number theory here, but just the beginning of it. But it'll be pretty useful when you learn about groups later. But so this is the common question, and the question is, when D is the GCD, the greatest common divisor, it's possible. So I'm not going to go over the proof, but let's go over examples. Yeah. So what is the greatest common divisor? So for example, 12 and 6, a divisor is like, you all know what a divisor is, right? Like divisor for these two, it could be 2 or 3, but what's the greatest one? The greatest one, this is called GCD. The greatest one is what? It's 6, right? 6 is the biggest number that divides 12 and divides 6. You all agree? Yeah, it's called Euclidean algorithm. So how do I find it? Well, you could use Euclidean algorithm. So let's do something more, non-trivial, like 14 and 10. How do you use Euclidean algorithm? Well, 14 is, how many times does 10 go to 14? It goes 1 time, right? So and then I have remainder 4. And what I do is I bring this to the left now, and I ask how many times does 4 go into 10? And that's 2, right? And then I bring the 4, these 2 down. So then I ask how many times does 2 go into 4? Well, 2 times, right? And once you hit 0, that top term is your GCD. Yeah. So your GCD is 2. I mean, obviously you didn't need the algorithm because the number is small. But I mean, when numbers get big, this is a nice algorithm. It runs like, if you're interested in code, it's like on order of like log something, log n. So now how can we go from here to here? You go backwards. So I write 2 is 10 minus 4 times 2. And then now I could rewrite 4, right? 4 is what? 4 is 14 minus 10, right? And then you want to keep the 14 and 10. So minus 2 times 14 minus 2 times 10. So 2 is 3 times 10 minus 2 times 14. And then you're done, right? So what I mean is my x and y in this case are, 3 and 2. Yeah, so if you use Euclidean algorithm, you get the GCD, and then and I guess some people call it reverse Euclidean algorithm, you get the linear combination. Yeah. So this will be important when we study groups. So, but this is just an example. Yeah. So another way to see this is 13 and 7. 13, obviously the GCD is 1, right? Because they're both prime. So 7 times 1, and then 7 is 6 times 1 plus 1. And then 6 is, let me just underline what I'm bringing down like before. 6 is 6 times 1 plus 0. So GCD is 1, right? And then obviously any multiple can be written as a linear combination of the two, right? So what I mean is this is, if you like, this is D, this is A, this is B in the question here. Yeah. So, and obviously you could write any multiple, right? 4 is, you just multiply by 2. So 6 times 10 minus 4 times 14. So it turns out if you're not, a multiple of the GCD, it cannot be written as a linear combination. And if you're interested more in this, take Math 180. Okay. Any questions so far? Plus. Okay. So let's move on. So the point now is to go over symmetries. Your professor wants you all to see symmetries before Wednesday. So let's go over that. So I'm not going to go over definition again because he told me not to. So just think of symmetries of an n-gon as reflections and rotations. So I don't know the history behind this, but you know what an n-gon is, right? Like a 5, this number of sides. So like a 5-gon is a pentagon, and then like six sides is hexagon, and then 8 sides is like octagon. So I mean, I don't know why they don't call 3-gon trigon. They call it a triangle, and a 4-gon they call it a square. But let's work with a square. Yeah. So the book tells you the symmetries of a triangle. So let's do a square. So in my notes, I don't know why I did this, but most people would do 3 here and then 4 here. Let's just go with my notes. I put the 3 here. So this is my vertex, right? These are my vertices. Vertex 1, vertex 2, vertex 3, vertex 4. So in the book, you're going to learn that for triangles, there's 6 possible type of symmetries. And for a square, there's 8. So what you're going to see is you can rotate 90 degrees, right? What happens when you rotate 90 degrees? So you get 3, 1, 2, 4, right? Or you could rotate 180 degrees. And then you get 4, 3, 2. If I mess up, just tell me. And then you could rotate 270, right? 270 degrees. And then you get, what is that? 2, 4, 3, 1. So I'm labeling where the vertices move, right? So here, like 1 gets moved to here, right? Hopefully you all get my notation, right? So this is where vertices move. So, and then what happens when you rotate 360? It stays the same, right? So it's 1, 2, 3, 4. So there's 4 rotations, possible rotations. And then how many reflections can you have? Well, how can I reflect? I could reflect, so let me just write 1, 2, 3, 4 here. I can reflect along this diagonal, right? So if I do that, what do I get? what moves? Well, I mean, nothing really moves for the 1 and 4, but if I reflect these two, right, these two get reflected. So I get 3 and 2, right? And then similarly, I can reflect along the other diagonal to get 4, 1, right? So let me just write reflections. And then I can reflect along the horizontal, right? Horizontal thing. So 1, 2, 3, 4. So in this case, 1 gets moved with 3, and 2 gets moved with 4, right? And lastly, you have this, the vertical. So in this case, 1 and 2 get switched, and 4 and 3 get switched. Now, question, why are these the possible, can you get any more, right? So you can ask, if rotation and reflections are symmetries, then any combination of them is a symmetry, right? So what we're going to notice, for if I just rotate, right, there can only be possibly 4, right? So there's nothing interesting going on. So the question is, what happens if you rotate and reflect? Right? If you rotate and reflect, and you end up with one of the 8 I listed above, and then if you reflect and reflect, and you end up with one of the 8, like those are all, right? So let's see what happens when you rotate and reflect, right? So let's do rotate 90 degrees. So 1, 2, 3, 4 gets mapped to 3, 1, 4, 2. Yeah. So 1, 2, 3, 4 gets mapped to 3, 1, 4, 2. So this is rotate 90 degrees. And then let's, oh no, how do you want to reflect? let's reflect along this diagonal. Yeah. So what happens then? What do I get? I get 2, 3, 1, 4, right? The 2 and 3 swap. So what does this end up to be? Does anyone see it? So what just happened here? Is this a rotation reflection? Yeah, it's what happened. So how do I go from here to here? Is it a rotation reflection? What is it? I basically swap these two. So like the 2 switch with the 1, and the 4 switch with the 3, right? What is that? That's a reflection, right? If I reflect along this line, right? The vertical line, the 2 gets mapped to 1, 1 gets mapped to 2, and then 4 gets mapped to 3, 3 gets mapped to 4. Yeah. So does everyone see that? Yeah, it's a reflection, right? So it turns out that rotation plus reflection is a reflection. The proof requires, I don't know if I should say it now, but it's it requires you to know about groups. But so let's just take it for a fact for now. Yeah. So from here, you could check. I mean, reflection is a bit easier. I mean, if you do two of the same reflections, you get back the original, right? I mean, if you reflect and then you reflect again, you get the original. So you can check that the combination of 2 reflections is a reflection. But really, this actually works for so what I want you to try at home is you can try 3D, 3 dimensions now. So again, in the book, there is the triangle has 6 symmetries, right? I think it's 3 rotations and 2 reflections, something like that. And then the square we just worked out has 8 symmetries, right? 4 rotations, I guess, and 4 reflections. Yeah. And so now the interesting thing, if you're interested more in these stuff, is the cube. The first, it's now this becomes highly non-trivial. It becomes very hard, right? So the result is that there are 24 symmetries. Now you might wonder why, there's so much. And the point is, you could rotate the cube many ways, right? And reflection now is no longer 2D, it's 3D, right? So basically, you can reflect along this diagonal, for example, right? I'm really bad at drawing, but you can see that this is like, this is a possible diagonal inside the cube, right? From this point to like this point. So like there, you can reflect along many more different diagonals, and you could rotate, not just 90 degrees, but you could rotate many more ways, right? So, and there are a lot more vertices to account for. So you could try it. You could look it up online. It's pretty cool. There are many different symmetries of a cube, and then you could try. It's pretty hard, but like tetrahedron, there's many more, right? Like there's tetrahedron, and then all those other shapes you learned in geometry, right? So I'm not gonna go over all of it, but yeah. Any questions? Oh, someone typed something right now. Yes. Yes, but we don't have the tools to prove it yet. It isn't rotation plus reflection, right? Because like the triangle, it's actually I guess I guess for an n-gon it's easier to describe, right? For what I mean is in general, no, right? I mean the tetrahedron, I probably don't even know like how many possible rotations and reflections there are. Yeah, but I mean for an n-gon it gets a bit easier, but in general, I mean I don't think so. So yeah, n-gon for sure. Yeah, so in 2D I could do it. So okay, any questions so far? I don't have much for today, but okay. So without further ado, I mean that's all I have for today. So do any of you have any questions? So again, if the important stuff today is I mean the quiz is on Thursdays. I'll post the quiz today sometime, and then you have all I did was just go over what he'll cover on Wednesday and give an example of an equivalence relation. So I guess for him, this one is, I mean, you can just check it, right? If A is equivalent to A because A minus A is 0, that's divisible by 3. And then A is equivalent to B. So implies B is equivalent to A. So this just means what? This just means A minus B. If A minus B is divisible by 3, right? B minus A is divisible by 3, right? Because it's just negative of A minus B divisible by 3. Sorry, by 3. And then you just check it, right? So if A is equivalent to B, B is equivalent to C, then you need to check then A is equivalent to C, right? So this just means A minus B divisible by 3, B minus C divisible by 3. So you need to check A minus C is divisible by 3, but you just sum it up, right? If these two are divisible by 3, then if you add, a minus b plus b minus c, that's a minus c, right? And the sum, if two things are both divisible by 3, then their sum also is, right? So it's pretty clear this is an equivalence relation. And I guess the thing to take away is equivalent relation partitions your set, yeah? So if you could divide your set to classes where, the class of an element in your set is, is defined to be an element of your equivalence relation, right? So basically just take all elements that are equivalent, put it in one class, and then take all elements that are equivalent, put in another class. So here, right, in the example of mod 12, take all elements of remainder 0 when dividing by 12, that's one class. Put all elements of remainder 1, that's one class. And then these partition your integers. Yeah. So any questions? I don't know. He posted homework, so the quiz should be easy. Trust me. If you understand what I went over today, you should have no problem doing the quiz. The homework might be a bit harder, I'm guessing, because I T8 for his 180 class. The homework should be a bit harder. Yeah, see, it's kind of hard for me to tell you, Jason, because we didn't really define what symmetry is yet. But just know for an n-gon, it's rotations and reflections for now. Yeah. I'm not sure. Yeah, because he makes the homework, so you have to wait for him to publish it. So for 180, he actually typed it up himself, I think, but he did take some from the book. Yeah. Okay. Any questions? Yeah, so like, for example, A and B belong to a class. Like B is in the class of A if A is equivalent to B. So basically, you put everything that are equivalent, equivalent means the equivalence relation, in the same class, pretty much. They'll submit the whole, I guess so, yeah. Right, so for example, Jason, like this one, the one he went over, I guess. I guess if the set is the integers, the class of 1, right? You have the class of 2, and I'm the class of 3 and nothing else, right? I'm guessing, yes. That should be all, right? Because any other number like 4, the class of 4 is the same as the class of 1, right? Because they are equivalent. Because when you subtract them, it's divisible by 3. And then like the class of 5 is equivalent to the class of 2. Because when you subtract them, they're divisible by 3. So they're equivalent. And then like the class of 6 is the same as the class of 3, because when you subtract, you get a multiple of 3. So there should only be 3 classes in this case. It's 1, 2, 3. Or if you like, you could choose a different one, right? Like 0, 1, 2. Do you get it? Or make sense? Makes sense, Jason? I don't want to formally define stuff because he didn't define it yet. So I'm just giving you examples. Hopefully you're good, Jason. Okay. Yeah. I'll post the quiz soon, and then I'll ask you on Wednesday if there's any trouble. Yes. So. No problem. Jason, what do you mean by A without it's? So I guess, what do you mean A without B? These are elements, right? Not sets. Yeah. How about this? Let me share. So, like for here, if I just erase this really quick, the class of one contains, you know, has all the integers 1, 4, 7, 10, 13, and then and then -2, -5, so forth. Yeah. And the class of two, basically every integer belongs to a certain class, right? So the class of two has 2, 5, 8, 11, -1, -4, so on and so forth. Yeah. So basically, you put everything that's equivalent to each other in the same class. So if A is equivalent to B, then the class of A contains B. So you could just take out B because the class of A already has B in it. They're equal pretty much.
When you take the elements of set A, but you don't include the elements from set B, is that A / B or A minus B? Or do they mean the same thing?
Oh, I thought you were asking about like I thought you were talking about like the elements here. Oh, you mean in general, right? Like you mean like if I given a set A and set B, like A.
Yeah, that way.
Oh yeah, so this would mean like the things in A without the things in A that are not in B, right?
Is that identical to A minus B?
Yeah, it is, but I guess I forgot which one is which, but with one of them, there's a when you write that, it's kind of assumed that they, how do I say it? I think one of them, it's sort of like assumed that one's like the bigger space, sort of, right? Like for example, like I forgot which one, but like yeah, it means the same thing, but like normally, like when I see something like this, I I think of A as like a bigger set containing B. You get what I mean?
So
Like
which way would textbooks like to say it?
honestly, don't worry about that. Just know it's defined as the things in A that's not in B. So these two, it's like the elements in A, not in B.
Can you explain class again? Class is the elements in an equivalence relation.
Yeah, so under an equivalence relation, you can, so let me just write this. Classes are, the best way to explain this are, I'll write it like this. I forgot the formal definition is in the book, but the way to see it is like collections of objects. So if I have a set A and I have the equivalence relation on A, like tilde on A, then our collection of objects that are equivalent, right, under the equivalence relation. under equivalence relation. So you have to have an equivalence relation first. So for the example was set is the integers, right? A is equivalent to B if and only if B minus A divisible by 3. So so you have three classes, right? You have the class of, like, I guess the collection. You have the class given by 1, 4, 7, 10, 13, so on and so forth, right? -2, ... right? You have the class of these objects, because all these objects are equivalent, right? I mean, if you take any two of them, they're equivalent because their difference is a multiple of 3. I mean, is divisible by 3. Agreed? Are you following me?
Are they objects or elements?
The elements of Z, if you like. Yeah. So these are, I mean, all these elements are equivalent. Agree? I mean, these are elements of Z, right? One is in Z. Yeah. They're elements of your set Z. So right, and they are equivalent. I mean, any two are equivalent because, because not equal, because 4 minus 1 divisible by 3, right? Yeah. So your first class, this is just notation. We just denote it by, we just pick one of the elements and we just write bracket. That's notation for, like, the class of 1. So this is notation. So the class of 1 is like all elements that are it's a collection of all elements divisible by 3. I mean, where, when you subtract 1 from it, it's divisible by 3. And then you have the class of 2, which is, this notation, but it's, it's the collection of, elements where, 2, 5, 8, 11, 14, so on and so forth, right? So it's just notation, yeah. So I could also write the class of 4 if you like. So I just pick one element in that set, and then I write class to the note. It's I mean, I have to have a notation for the class, right? Mm-hmm. So that's just how most books denote it as. Are you still here? Or I forgot who was talking to me. Oh, okay. Okay. Are you good, Jason? Your mic is off. Yeah, basically just think of classes. You put everything that's, oh, I hear you now.
I didn't like how he said subset.
Who?
Subset. I learned it as there's subset, proper subset, and his notation of it's subset, but it's not, that element is not included or something. His notation the subset, he just draws it as a C. And I've seen it, subset is a C with a line below it.
Oh, yeah, that's just notation. But from what you said, this, or if A is a subset of B, some people are like this, some people are like this. But
Yeah.
the reason we put a line is because when we write not strict, I mean, when I say strict, we write this. This means strictly, strictly. Yeah, so it's because subset could mean the set could still be the same, right? Like A can be equal to B, right? When you write subset, because if A is equal to B, like A is still a subset of B.
So the
So
top right one, a subset of B, that means A can equal B. But the top left is A is a subset of B, but A is not equal to B.
I normally see this for like the not equal. Yeah, I'm saying this should be either or, I'm guessing.
Yeah, I've seen them both ways.
Yeah, these two just means like A subset B. This means, see, when I put the line, it means like not, right? So this means like A subset B and A not equal to B.
So is there such thing as a proper subset? Well, how would you define proper subset?
That is that's what it means to be a proper subset, right? When you're a subset and you're not equal. This is proper, right? Proper subset. That's what it means, right?
And both the top ones are just subset.
So the top one, it might not be proper, right? Because it could be equal.
Correct, but they're the same thing, the C or the C with a line below.
Yeah. That should be true. I tend to use this. So if you're worried, I tend to use that. I tend to use this one.
Yeah, that's what I'm used to as well.
Yeah.
So as long as we don't get docked off too many points on the final exam for that.
No. In fact, I think you'll be using a different notation because we won't really be working with sets. We'll be working with groups. Groups have a different notation, so you probably won't be seeing just sets anymore after like Friday.
Can you explain the elements of the class? Or the class is the elements of an equivalence relation.
It's the how do I say this? Yeah, pretty much. I mean, there's a formal definition in the book. I just want to give you examples of clear. I mean, because the definition might not be very intriguing. So I gave you examples of like how you should view it. Let me see where is the, well, sorry, bookmarks. Where's bookmarks? Hold on. Something is I thought I added it in the bookmarks, but where is triple E? Yeah, see, the professor still hasn't added me to the triple E thing, so I have to access the web through like schedule of classes, which is really annoying. 120. hope he went over all that set theory stuff, so I don't have to go over that. But yeah, see, it's defined like this. Not very. Can you all see my screen right now? Or yeah, it's the set of things that are equivalent, right? It's called the equivalence class. It's right here. Right, it's just the set of things that are equivalent. So in our case, right, our big X is the integers. So basically, if you just choose, it's a set of things that are equivalent. So you just choose all the things that are, when their difference are multiples of 3. It's like the collection of elements in Z, such that it's equivalent. And then what I talked about was partition. Partition means like it's pretty much divides up Z into your classes. Pretty much divide up all of the integers. The definition itself is not very intriguing.
Can we think of that as the formal definition?
This is the formal definition. Yes.
Okay.
So I'm just saying in our see the class of X, so they just choose an element to be like, to represent it, right? So the class of, if I go back, so here, like the class of 1 is, if you want to use their notation, it's the set of Y in Z such that Y is equivalent to 1. But what is that, right? These are the set of elements Y and Z such that Y minus 1 divisible by 3, right? And then if you think about it, it's what I wrote here, right? It's like ... -2, 1, 4, 7, 10, 13, so on and so forth, right? It's just that. I'm just doing it for a particular example to make things more clear, I guess. Good. So for those of you, if any of you are still here, is both the live lecture and the video thing gonna follow the, I mean, is it both new content, or is it like, or is live lecture discuss stuff from video, from previous video, and then video is like new content? Anyone? Okay, let me stop recording.